Oh man, I wish you told me that earlier. Okay, well, all right. So again, as I was saying, um, the recognizer is the part that parses through a text and makes sense of that text and try to fit it with the grammar that we've given. And if it doesn't fit, then basically we've got a syntactical error. Okay, in case this was a compiler, and this is what all compilers do, is that they're big fat recognizers. Now, after you recognize it, okay, there's other parts of the programming language that then take on to actually execute. But the first thing it does, the compiler, is that it sees what you've written. Does it actually fit into the grammar? Because if it doesn't fit into the grammar, there's no point in trying to make sense of it. Okay, and actually execute the statements based on the interpreter that we programmed little later previously. Okay, and this is why when you write something that syntactically is incorrect in a Java programming language and a Java IDE, before you even click run, it gives you that little squiggly red line because it knows, okay, that you've done something wrong because what you've just written, it doesn't fit the grammar, so there's no point in waiting. Okay, there's no point in waiting for you to attempt to execute. The next component, the next use of a grammar is that you can actually create strings, automatically create strings based on the grammar. So I would give you the grammar and then I would give that to the generator, and the generator would then start to create maybe random or semi-random strings based on that grammar. And obviously the strings that will be created are valid because they are based on the grammar that I was actually given. Okay, probably the second one is a little bit less common. The top one is what all parsers are made of, and compilers are one big fat compiler, parsers. So that's what they all do. Okay, have you actually anybody actually know or dealt with a parser before? At least know what a parser is? Okay, I take that as a no. Yeah, JSON parser, yeah, that works as well. Yeah, XML parsers, yeah, good job. So they're really the same thing, but an XML parser maybe not necessarily looking for syntactical errors, it's looking for structural errors. Okay, same thing as a JSON parser. In case you give it something that is not structurally constructed correctly, then it tells you that there's something off over here. With a programming language and a compiler, it's looking to say that what you've written is syntactically incorrect and it won't actually run. All right, so now we're thinking about testing. Okay, we said the whole purpose of this chapter is we're looking at testing from a completely different perspective. We're not looking at the structure of the code like we did in graph coverage. We're not looking at the input space and breaking it down like we did in input space partitioning in chapter 6. We're looking at the actual syntax. And so we need to cover the syntax. Okay, we said actually two things. We will try to cover all of the syntax, okay, to see if there is some part of the syntax that is there. We got to be able to cover it, okay, and we got to cover it in different ways. The second part is we're going to mess up with the syntax, with the grammar, I mean, and then see if also things are working. In other words, in the second half, which we haven't gotten to yet, we're checking if the software is not doing what it's not supposed to do. But we're still at the first half. Okay, we're still in making sure that the software is doing what it's supposed to do. So we got our syntax. Okay, we got to make sure that we have covered it. Now we can cover it in one or two ways. Okay, the first way is something called terminal symbol coverage, and I just make sure I touch each one of those terminal symbols. And the other one is called production coverage. Okay. And terminal symbol is focusing on the terminal symbols that I can actually see. Because remember, when I'm looking, let me see. Okay. When I'm looking at a grammar, this itself, back over here. This part over here, because it's a non-terminal, it's never gonna show up. So a way I can say, well, okay, let me just focus on the things that can actually show up in the final strings. These are the terminal symbols, and I just want to make sure that each one of those terminal symbols can show up. Okay, and this sort of coverage criteria is called the terminal symbol coverage. Okay, production coverage looks at this part of here as well, in addition to the bottom part. So the bottom part is TSC, okay, and the top part with the bottom part is called the PDC. Okay, now we said that the top half is never going to show as a string. Yes, sure, but we're looking at to touch each one of those as we go down and make sure that as we're going down, okay, into the generation of these terminal symbols, that we're actually touching each one of these production rules, the non-terminal production rules beforehand. So let me give you an example over here. Okay, if I had these following ground strings, okay, you know, A, what does that cover? Okay, well, it covers this over here. Okay, if I write down all of the different symbols that comes a letter, okay, we get all of these over there. Okay, great. Type. If I go 0, that means I got this one. Good. All right. And if I go 0 all the way to 9, then I've covered all these at the bottom. Okay, I still got a problem. I haven't covered those operations over there. So what do I do to cover them? Okay, sure, I can go 1 plus 2, 3 minus 4, 5 multiplied by 6, 7 divided by 8. That would have covered this one, this one, this one, that one, right? Okay, and as such, all of these ground strings that I have produced, okay, would cover my TSC. All right, but those ones that I've covered, they don't actually cover all of the production rules that I had over here. Which one did I actually cover? Okay, when I went A, and it was, you know, different letters. Okay, I did those ones. Okay, and I also did which one? ID followed by letter. Okay, because it was single letter. I didn't actually do this one. All right. Next up, when I did 1 to 9, I'm covering those ones. All right, which when I go up, I realize that I have started from here, then I got digit. I didn't actually do this one. Okay, next up, when I did A plus B, okay, or 1 minus 3, okay, I realize I'm doing this one, followed by either this one or that one. Okay, and that means that the initial set of test cases that I've produced, in other words, ground strings that I've produced, it has covered everything, this one, this one, this one, and from the production rule covered this one, that one, this one, but it didn't actually cover this one or that one. So if I ask you, give me a test set that would satisfy TSC, all right, satisfies TSC, but doesn't satisfy PDC, all right, you would give me the test cases that we said before, you know, just the A to the Z, the 1 to the 9, and followed by any 4 operation that covers the different 4 mathematical operations. So 1 plus 2, 3 minus 4, 5 multiplied by 6, 7 divided by 8. Okay. Now, in order to cover PDC, I need something to satisfy this one and something to satisfy that one. Okay. So this basically means I need something that is more than one letter. So if I have something called AB, that would satisfy this. And for the digit num, I need something that is more than one number. So maybe 1, 2. But this over here on itself is not a valid string because it doesn't fit into that grammar. I can't fit it. All right, the closest thing I can fit it with is this one over here. So I can put any symbol. If I put, like, say, a plus, then it fits over at this top symbol over there. And with it, with the addition of AB plus 1, 2, I would have covered PDC in addition to my TSC. All right. Does that make sense for everybody, guys? All right, that's good, because I have to admit this is actually very complicated. Okay, it's not easy. So if you don't understand, don't hesitate to ask. I mean, it is a thick lecture, to be honest. Okay. Now we said we have PDC, sorry, TSC, and then PDC. Okay, this one over here is sometimes called PC. Let me just go over here. PC or PDC. Okay. And in a way, you can think as TSC, when it comes to graph coverage, is the nodes, okay, the actual terminals, and the PDC or PC is the one with the combinations, combining the different nodes together. So it's kind of like the edge coverage, okay? Another criteria is called the derivation coverage, okay? Now, derivation coverage, if we go back to over here, to this over here, so we said we had, for example, when we're doing PDC, we said we did a 1, 2, AB plus 1, 2 to cover this one along with this one and that one. But derivation coverage means it's not just enough for me to go through the production rule itself, but I gotta go through every possible derivation that can exist. Now, had I had a language that says X could have been 0 or 1, okay, 0 or 1, should I say? Then all the possible derivations would be one time it's a 0 and one time it's a 1, okay? It's not a big deal, okay? However, if I have something like this one over here, the number of derivation, the possible derivation are absolutely impossible, infinite, okay? I can have AB, I can have ABC plus 1, 2, I can have ABE plus 3, 4, okay? If I look at all the possible derivations that I would get with this relatively very small language, we get an infinite, we'll need an infinite number of test cases. So a lot of the times, the derivation coverage, while obviously stronger than PDC, it's usually impossible. It's only possible if I have a very, very, very small language, okay? All right, so if I have a language that says, for example, A could have been, or sorry, a code would be an A, B, C, okay? A, for example, is 0 or 1, B is 0, 0 or 1, and then C is also 0 or 1. So I got a maximum of 8 possible combination. Again, it's still doable, okay? But it's got to be of something extremely small as such. Otherwise, you end up with an extremely large and infeasible, impractical number of test cases, or maybe even infinite, okay? So again, just to wrap up, okay, we said we got TSC. Got a question over here. So if any variable has a recursion in it, this can't be done. Yeah, that's actually true. Okay, so remember, Abdurrahman, when we were doing, for example, the binary, just the binary example that we did last lecture, or at the beginning of this lecture, when we were doing the even strings, even x's language. Okay, basically, I have infinite. Okay, I have an infinite set of derivations that I can possibly have done. Okay, there's not a possible set. Okay. So anyway, we said TSC is subsumed by PDC. Sometimes you'll see it in the slide called PC, which is subsumed by DC, and DC, and as I said before, tends to be impractical. So, we'll stop at PDC, so to speak. Okay. So when we were looking at terminal symbols, okay, remember the counting that we did before? We had 40, I think it was the 26. We had the 26 plus 10 numbers plus the 4 operations. They gave us 40. Okay. If we added the production coverage, we had, remember, it was 3 at the top, followed by 2, followed by 2. So there was 7. Okay. So now they're giving me 47. Okay. So until 47, we're okay. All right. Anything beyond 47, or not anything beyond 47, had we done derivation coverage, then it would have definitely been non-practical with an infinite number of test cases, even for a toy language like the one that we have for the algebraic expressions, right? So any questions about this, guys, before I move on? Is that clear for everyone so far? I'd like to hear it back from you guys because this is a tough lecture, so it's only gonna get more complicated. Okay, good, good. Like, if you have questions, again, please feel free to just text, and I'll be sure to respond. Okay. All right. One more question. Okay. How many test cases are there for TSC? Okay. So for the example that we had, yeah, Abdurrahman, we had 40. Okay. So again, we're going back over here. And TSC basically, Abdurrahman says, touch each one over here. And when we did the counting, remember it was 4 at the top over here, 4 operators followed by 26 letters followed by 10. So 4 plus 26 plus 10, that gives me, I would have done it in 40. Test cases. Okay. These are test requirements. Is that what you asked? Let me see again. How many? Yeah, test case. Okay. So let's think about it. Well, I didn't compute it, Abdurrahman. There's no any particular way to compute it. It's not about the number of test cases, but more than it's about what are the test requirements. Okay. Basically, what you want to do is the minimum number. Okay. So, I think you'll need more than 4, Abdurrahman. Because remember, every digit and every letter has to show up. Okay. Every letter has to show up. It's not just a case of you combine the plus, the minus, and the supplement into one long test. Yeah, that actually works. I didn't think of this. I was still thinking about one single letter at a time. So I was still thinking about trying to satisfy TSC without satisfying PDC. All right. So if I asked you to do this without satisfying PDC, you probably needed more test cases. But yeah, if we're not really paying attention to the PDC and we're okay with covering it as well, then yeah, we could have just done it in 4. Matter of fact, we could have probably done it in less than 4. Yeah, actually, Abdurrahman, we could have done it in less than 4. We could actually done it in 1. All right. Because remember, an expression, this last one over here, it itself could be decomposed into another expression, operation expression. Okay. In other words, I can go AB plus CD plus FG. Anyway, this is not really the focus here, but But the focus here is to realize what are the test requirements that we have. Okay. All right. Now I want to get something clear before I move on. Is that, whoops, two different terminologies. Okay, the first of which is the grammar, which is what we're looking at with the BNF, and something called the ground string. Okay, so in terms of software, the grammar is the actual syntax rules, okay, of a program, and if we mess it up, okay, then we are messing up with a grammar that would produce something that could be or may not be syntactically correct. And if it's syntactically incorrect, then we're really actually testing the compiler to make sure that the compiler is doing its job. The ground string is an instance of the grammar, okay? Any instance, any derivation. So sometimes we refer to it as a derivation. Sometimes we refer to it as a ground string. Now, when it comes to the world of software, the ground string is that the actual program. It's what you actually see in front of you on the screen when you write a Java program. That's ground string, okay? Every single Java program that has been written is an instance and an example of the Java grammar that is produced, that we have one and one time only, okay? So remember we said we have two parts to the Holy Grail, and you know, the first of which is making sure that the software is doing what it's supposed to do. Second of which is making sure that the software is not doing what it's not supposed to do. So if we do mess up with the ground string, again, one of few things may happen. I might end up with a messed up string that is syntactically incorrect. And again, that will be the job left up to the compiler to make sure that it is working. It could be a ground string that is syntactically correct, but has a different behavior. And I would actually see the different behavior as a bug. And I'm happy to see this bug because it is showing a different result than the proper code. Okay. And then finally, the third situation, rather unlikely, but it could happen, that I could actually change the code, but then result in a new code that is doing the same exact thing that the old code was doing, which means that didn't really help me much. Okay. Now, this all comes to the concept of mutation. Okay. Now, the word mutant means you've taken something original and you've edited it. Okay. You've made a different version of it that is outside the norm, a different version of it that is not the way it was supposed to be. Okay. Okay, so it's not just here's a newer version that is doing more functionalities or anything like that. No, it's a different version of something original in a form that is not supposed to be. Okay. So I'm not sure. I know it was back in the day when I was a kid. But does anybody know? Let me see if I can produce this. I'm gonna do a screen share here for a second, just a moment. Well, wouldn't you know, it's not actually loading. I mean, I had it ready, but now that I want to show it to you, it's taking forever to load up. Anyway, there we go. Everybody knows these guys over here? You know what they're called? This cartoon. Yeah. Anybody can take a guess. What are they called? You want to tell me what are they called? Write it in the text. Yeah, everybody knows them as Ninja Turtles, but they're actually called Mutant Ninja Turtles, right? That's the official name for them. They're teenage, well, because they're young, teenage mutant. Okay, so basically, mutant means they're turtles, but something odd has happened to them. That yes, they're still turtles, but they're definitely a messed up version of I mean, and that's why in the real world you don't actually see turtles with massive muscles wearing eye masks and with talking to each other and such, right? So they're called mutant ninja turtles, and I apologize for the long time it took to load. I wasn't really expecting that to happen, but anyway, you know. So what are we gonna do when we're doing mutation testing? Okay, we have a set of rules. Okay, and these rules are called mutation operators. Okay, these are the actual ways I mess up with something. Okay, and I can apply it to either the grammar or I can apply it to the actual ground string. Okay, so I can apply it to the grammar or the ground string. And by systematically applying those mutation operators to the syntax, okay, or to the object, I end up with mutated strings or mutated grammars. In simple terms, we are systematically, okay, where does the word systematically come from? From the word mutation operators. Defining and implementing ways to mess up, okay, what is defined as proper, with the purpose of generating invalid derivations. Okay. Right. I might have messed something up. Here's the key word. And I ended up with a valid derivation. Okay. And I end up with a valid derivation. But that's not really the purpose here. I want to end up with an invalid derivation, because if I have an invalid derivation, then it's probably going to exhibit a different behavior than the proper code. Those invalid derivations should be detected as errors by the software under test. So we're making sure that the software is not doing what it's not supposed to do. Now, in lay terms, imagine this scenario has happened to you, huh? You've written a piece of software and you finished it. You feel you finished it, and then you've written 30 test cases, and all 30 test cases pass. And before you submit, you say, I'm gonna go use the bathroom and come back, and after I come back, I'll submit it. All right. But as you're in the bathroom, you have a friend, he's a practical joker, a prankster, and then they for funsies, they come in and they mess up your code. All right. And unfortunately, he didn't save the older version of the code, and you can't retrieve it. So the first thing you do is, obviously after getting a heart attack, is you'll say, and you yell at your friend and you say, this is not a funny joke and so on. The first thing you want to do is, what's the first thing you're going to do? Let me actually ask you that. So you came back from the bathroom, your friend, test, exactly. Your friend, so which test are you going to run? The 30 tests, Abdurrahman, right? Those 30 tests that you've done before you left and went to the bathroom, correct? All right, exactly, right? Because that's kind of like your measure of confidence, okay? Those 30 tests that I had, I'm gonna run them again and then see if they work. Well, you ran them, Abdul Rahman, okay? But to your surprise, the 30 tests actually passed. The 30 test has passed with the messed up version, the mutated version of the code that your friend has left you with. As happy as you are, still that gives you an uneasy feeling, okay? An uneasy feeling. You say, that's weird, you know, when I gave my code input 1 and 2, it gave me a particular output 1, and then we flipped up the code, I give it input 1 and 2, and it still gives me the same output. What that tells you is, okay, the 30 test cases are working, but surely other test cases may not work. Okay. Right. And this is why mutation testing is important. Matter of fact, is the golden standard in the industry right now. Okay. Right. And yeah, that's really the main goal of mutation testing is you realize that the reason why the same 30 test cases have worked is because those 30 test cases have covered your code in a certain way, have covered your code in a certain way, but has left parts of your code uncovered. Okay, parts of possible ways your code could be executed uncovered. And as those ones that are uncovered, that probably your friend has messed up with, and that's why, despite your friend messing up with that part of the code, all right, it didn't actually affect the other parts of the code where the original test cases that you've done before you went to the bathroom are actually touching. And this is why when you came back and you ran the same 30 test cases again, they actually worked. All right. So what you should be hoping for as a tester, not Abdurrahman, not the person who I'm moving away from that example. Okay, I've written code, right? I've given it a 4 and a 5. It gives me, for example, 36. Fine. Now, my hope is that if I mess up with the code inside, that when I give it a 4 and a 5, it no longer gives me a 36. 36, I mean. I want it to give me something different. Okay. And when it gives me something different, all right, then this is sort of like the confidence that you're building that is not doing what it's not supposed to do. Okay. So let's go back over here. All right, let me close this. So when we're dealing with grammar-based testing, this is the first half of this chapter where we're dealing with the unmutated derivations. Okay, just like we had before, AB plus 1, 2. That's an unmutated derivation, and I do testing for it, and this is the traditional testing that we've been doing since SC100. Okay. Then comes the fun part, the mutation testing, which begins in this half. The mutation testing, okay, it's all about creating invalid strings. Okay. And as we'll see in a moment, we might actually mutate and still end up with a valid string, but that's not really the purpose. Okay. Had we achieved the purpose of creating invalid strings, we could be doing it in 2 ways. We could be creating invalid strings based on mutating the grammar, or we could be doing mutated derivation based on mutating the actual ground string. Okay, so the grammar means I'm going to actually look at that BNF. I'm going to mess up the BNF itself. And had I created an invalid derivation, or even just created a mutation of that grammar, think about it this way. The compiler at this point might actually compile something that is syntactically incorrect. All right. So it's a very inverse way of thinking about things. All right. And when it comes to the ground strings, x equals x plus 1, semicolon, I could mess it up to have something that's invalid. So, for example, x space x plus 1, that's invalid. Or I could have done something that is valid. For example, instead of x equals x plus 1, I could have changed it to x equals x plus 2. Now, x equals x plus 2 is still a valid string and should compile, right? However, it might produce a bug at the end, but still it's a valid string, right? Now, just to clear things up, why is this? Okay, we said we're going to have mutation operators, okay, and it defines a rule, okay, a systematic approach to mess up and create a different variation of a grammar or a ground string, and the result of it is the mutant. Okay, so think of the potion that these little turtles have drank when they were young. The potion is the mutation operator. Okay, the little turtles were the original grammar or ground string, and then when they drank it, they became mutant ninja turtles. Okay, so the mutant is the produced messed up version of the original. So we apply the operators to a grammar or a ground string, and then we end up with a mutated grammar or similarly a mutated ground string. Okay, there could be many different types of mutation operators. When I'm applying it to a grammar, I could have mutation operator 1. Okay, if I apply it to the grammar, it's going to give me a mutant grammar 1. If I apply a different operator to the same grammar, it's going to give me a completely different mutant grammar 2. Okay, and likewise, mutation operator 3 gives me mutant grammar 3. Similarly with ground strings, 1 produces mutant ground string 1, operator 2, mutant ground string 2, operator 3, and so on. You can have as many as I want. An obvious question at this point you should have is, should we be having more than one operator, mutating operator applied at the same time? You probably wouldn't want to do that, okay? Because you might end up with the unlikely situation that the mutation operators might actually cancel each other out. Okay, for example, you have x equals 5. Okay, and then one mutation operator comes and says -1, another mutation operator comes in and says +1. Well, we've done nothing. So they cancel each other out. Despite actually applying two different operators, they end up canceling each other out. Okay, and in general, you want to have one factor so that any observation that you see as a result, you know that it's attributed to this one and one only factor. All right, so that when you actually see a different output, you know it's because of that particular mutant. You're not wondering, why am I seeing this different output? Am I seeing this different output because of mutant operator 1 or is it mutant operator 2? You don't want to do, you only want to be in this situation where you're wondering which one exactly are you is resulting in that different output. Okay, so you might really want to always have one operator being applied at one point only. All right, so mutations over the grammar can be considered with the purpose of generating invalid derivations. These could be recognized as errors. Okay, different examples. I can delete a terminal or a non-terminal. Oops. Right. I can duplicate a terminal or non-terminal. I can replace a terminal with something else. I can replace a non-terminal with something else. Okay. Here's an example. Okay. This is my original grammar. And I'm going to apply mutation deletion by deleting terminals and non-terminals. Okay. So I'm going to take this line over here, okay, where it says expression ID num expression operator expression. All right. One way I can do it is I can delete the whole thing, or I can take this one over here and then just delete the first one. I can take this thing over here and I can delete the middle part and I end up with this, or I can take this over here and then I can end up with and I delete, sorry, the last one. I end up with just expression operators, and with it I can start to derive, based on these messed up grammars, actual derivations, something that is empty, plus AA, 12 plus, and so on. All right. Some of these derivation could be valid. Some of the other derivation may not be valid. Okay. Let's take a look at a different example over here. We're gonna apply mutation to this BNF by doing duplication this time. Okay. Over this line over here, the expression. Okay, let's take a look at some of these examples. Okay, so here I'm going to take ID, I'm going to duplicate it, ID, num, duplicate it, num, expression, op expression, I can duplicate, say an expression, that's a duplication, op expression, or expression, op expression, or expression, op expression. All right, and so with these 5, A, B, C, D, E, I want to create derivations. All right, some of those derivations might actually end up being valid, some of them may not be valid. So ID I can have AA, num I can have 1 2 1 2. AA and 1 1 2 1 3 is actually valid derivation. Okay, this is just an expression and this is a different expression. So here's the thing, I might actually end up messing with the grammar, but still end up producing something that compiles. Okay, but I might end up messing the grammar and result with something as A plus 1A plus B. That's an invalid string. Okay, and again, A plus plus 10, that's for this one over here. That's invalid as well. And for this one is A plus 1A, that will be invalid as well. So those numbers 3, 4, and 5 are not supposed to get by the compiler. And had they got by the compiler, then there's something wrong. Okay, then the compiler is not doing what it's supposed to do. Okay, and you can think of this A plus 1A plus B from the perspective of the compiler testing, is that we're making sure that the compiler is not doing what it's not supposed to do. All right, I'm gonna stop here for a second, guys. Is that clear for everyone, what I was saying? So Abdurrahman is asking, why is AA valid? So AA basically, Abdurrahman, is just two different expressions. Huh? This A is an ID, okay, going up actually all the way up over here. And this A is a different expression for the same production rule. You get it now, Abdurrahman? All right, just think of this as two different expressions. One is just an ID, and the other one is an ID. An ID that then later on turns into letter, and this ID then later on turns into letter. No. It's just two different. Okay. So Abdurrahman here. This is not the same as this over here. Okay. this is ID space ID. Okay, so it's something different here. And even if we had AA, by the way, that's still a valid expression. And even if we remove the space, it's still a valid expression. Okay? Because why is it a valid expression? Okay, I got AA over here. Let's work it out. Oh, wait a second. Get AA over here. Okay. I look at, let me just close this. I look at over here and realize it fits over this one. But then as I go down over here, I realize it fits this one over there. Okay, and then it's going to recursively go back over here, and then it goes to the letter. So this is the second A, and I would have had a valid string. I'm confused about space. I'm pleased we didn't add a space. Yeah, I know. You know, what can I say? I mean, it's not really a rule per se or anything like that. Think of it, okay, think of it, Abdurrahman, just to make it simpler for you. Assume there wasn't a space over here. Okay, whoops. Assume there wasn't a space. All right. Where is it? Assuming these are stuck together. All right, just like this one over here. The one on the A, maybe the spacing in the slide is a little bit excessive, but right. So this is what they look like had they been touching each other. But anyway, you know, it's still the same concept applies. All right. I just don't want you to be over hinged on the spacing matter. Okay. Type. Now mutation, program-based mutation, which is a fancy way, which is a fancy way of saying ground string mutation, is when I take an actual program, a valid program, and I mutate it. So I got a for loop over here, and it says int I equals 0. I mutated, and I increment the I by 1. So this mutation operator would say increment the initial position of a for loop by 1. Okay, and I look at a piece of code, I search for the for loop, search for the starting position, and whatever the starting position is, I increment it by 1. All right, this should produce a different output now when I run that code, the new code. Okay, I've introduced a fault by mutating the code. Remember this from the beginning of the year when we're talking about faults and errors and failures? We'll notice that the same concepts actually apply over here. All right. Now, what's the difference between the first for loop and the second for loop? Right. The first for loop, it covers the entire array of X. The second for loop, it covers all of the array of X except for the first cell. Okay, now, if the bug that I have has something related to other cells in the array, other cells other than the first cell, then the output of the first for loop and the second for loop would have been the same. All right, the output of the first one and the second one would have been the same, right? But if this thing, the issue that would have exposed that fault is related to the first cell, then the output would have been different, okay? And it's the producing of the different outputs is what we're looking for, okay? Okay, so you're saying you changed the code. So changing of the code is supposed to produce different results. My goal here is to actually make the software produce the different results, okay? Because if I run 50 different tests, like the 30 that you had before you went to the bathroom, and they're still producing the same output, then there's something missing. Something is off. I know I've changed the code. It should give me different output. Why is it still giving me the same output? I need to show that what I've actually done and the mess up that I've done to the code makes a difference, so that I can show that what I had before was the proper way of doing things. And the same actually concept applies when we were dealing with the change in the grammar. When I had something like the AA over here, or 1213, I'm producing the same output. How? With the original grammar, AA would have passed by the compiler. With the new grammar, AA would have still passed with the same compiler. At this point, I'm worried about the compiler, because I just changed the grammar rules and the compiler kept saying, yes, everything is good, everything is okay. It's only when I hit 3, 4, and 5, and the compiler said, something is wrong, that now I feel a bit more confident, okay? All right, so if the length of X, say, was 5 cells, right? There was a number, I'm counting the number of zeros, and then there's only 1 0. I'm assuming there's only 1 0, but that 0 was in the 5th cell. It's going to produce the same output. So I'm not really doing a good job of exposing the change that happened in the code, okay? And I would say that, and I'd be worried that, I've done something originally wrong, and because of that, it's not actually showing any differences in my code. However, had I made a test case where I put that 0 at the first cell, it would have produced a different output. It would have produced a different output. And with this, I have something called, I create the different mutants, okay? So here I am, I've got this original code. It takes in 2 different variables, X and Y, and basically checks which one is the smaller one, and then it returns the small one. So if X is smaller than Y, it returns X, otherwise it returns Y, which is at this point would have been equal to X in case it was equal to. And obviously, if it fails because it's equal to or bigger, then it just returns Y anyways. All right. I've created 3 different mutants, M1, M2, and M3. And the first one, I've changed the if condition over here, made it bigger than or equal, and then smaller than or equal. And then the third one, I didn't even touch the if statement. I just changed that line over here and the else. And instead of it being Y, I made it B equals minus Y. All right, so what I want to do is I want to produce tests that gives me a different output, okay? All right, and when I produce that different output, this is what I would say I would have actually killed a mutant. So given a mutant M for a particular derivation, all right, and I have a particular test, I would say that that test have killed the mutant if the output T on that derivation is different than the output T on the muted. Okay. The derivation D may be presented by the list of productions or by the final string. So in other words, I got a grammar over here, right? I have a mutant operator. I applied it to the grammar and I produced a mutant grammar. Okay, good. Now I'm going to create a test and apply the same test on the grammar and the mutant grammar. Each one of them is going to give me a result. Had I had a different output, then I would say I have killed that mutant. Same thing applies with ground strings. All right, I have a mutant operation. I apply to the ground string, it produces a mutated ground string. Right, then I have a test. Same test I apply to both the ground string and the mutant ground string. They will produce outputs. If the outputs are different, then I would say I would have actually killed the mutant. So back again to this example that we had over here, okay, about the operator, sorry, that for loop, no, this one. Okay, yeah, this one over here, sorry. So this is my original code, all right. I'm returning something, and each time I'm going to return something, right? I want to have a test case, create test cases that should produce different results. Okay? If it produces a different result, then I would have say, then M1 produced a different result than the original code, then it would have killed M1. M2 produced a different result than the original code, then it would have killed M2, and so on. Okay, I have 3 test cases. Let's see which one these are going to kill. So the first test case gives me x equal to 0 and y equals to 0. Okay, so I'm going to put x over here and y over here. I'm going to say x, is it smaller than y? No, go over here, return the v, which is equal to the y, so it returns a 0. Okay, so what I want to do here is I want to write down okay, well, I didn't actually do it yet, so I'm gonna check Abdurrahman. Okay. But basically, I'm gonna write down that it has killed the output for test number 1 is 0. Okay, what is the output over here, guys? Can you run the code for me here? No, give me a number. Don't tell me why. So I put a 0 and a 0 over here. What's the return? Is x is bigger? Yeah, it's still a 0. So if it's still a 0, yeah, Abdurrahman, then I didn't actually kill mutant 1 by this test case. Okay, what about M2? What's the output? Yeah, exactly. It's about the failure, yes. M2, guys, anybody else? It's not that hard. It's a very simple part of code. Give it x equals 0, y equals 0. What's the output? 0. Okay, what about M3? 0. So this was a very poor test. It didn't actually expose anything. So it's none. Okay, so let's switch it up a little bit. Okay, we're running out of time over here. So what I want you to do is, Okay, I'm just gonna give you the answers to this. Next up, what we're gonna do is we're gonna give x equals 0, y equals 1, oops, y equals 1 for this test case over here. And then we'll realize that this gives something different than than the original test case, but this one gives me the same and the same, so I wasn't able to kill. All right. Test case 3. All right, I give x2 and y. So this the y is actually smaller than the x. I realize that with M3 and an M1, it gives me different outputs. So I would have killed M1 and M3. And one thing that I will notice that it doesn't matter what the test cases that I would do, I could never produce a test case that would kill M2. And because the mutation that I ended up with, despite being unlikely, I ended up creating a mutant M2 that is functionally what we call functionally equivalent to M1, to the original code. Okay. In other words, had I had something like say x equals 5, that's the original code, and I come up with a mutation that just went +1 -1, well, it's always going to be the same. It's always going to be functionally exactly the same. So the mutation didn't actually do anything. It still is functionally equivalent, 100% equivalent to the original code, despite it being actually different. All right. And that would be the case of I actually have a poor mutant. A poor mutant, the design of the mutation itself is bad. So I got two things here. I want to have a good design for the mutation, okay, that I end up actually creating code that is functionally different. And then I need to have a good design for my test case to actually expose the mutant that I've actually created. All right, is that clear for everyone, guys? That makes sense? Okay. So that's gonna be it for today. I'll see you inshallah on Monday. I think Monday's our exam, صح?